Okay, so you should put in your attendances, first of all. Good. All right. So yesterday I shared with you the evaluation of quiz 1. Just just to let you know that the mid semester is on 22nd August, right? So did you check the routine? So mid semester for PH 603. Sorry, not 22nd September. So from 10 a.m. Okay. So the maximum time you would be allowed, uh, depending on the number of questions I give, would be 2 hours, okay, including everything, including submission and scanning and so on and so forth. So remember that no extra time will be allowed. And there will be some bonus marks for timely submission as well. So if you do not do that, then no considerations will be done on mid-semester. Hold on a second. All right. So please arrange accordingly so that you do not have a delay on submission. And I shared the quiz evaluations yesterday. Hopefully, all of you have checked that. So, do you have any queries regarding that? Okay. So, anyways, hopefully, most of you will do much better in the mid semester. So, we should prepare. So, today, I'm going to discuss canonical transformation and its relation to Poisson bracket. So, uh, canonical transformation and Poisson brackets. Now, so there are two equivalent statements here. So the first statement is that Poisson bracket do not change under canonical transformation. So you have number one theorem is that so PVs are invariant under canonical transformation. And if you go to the reverse statement, the reverse statement is that if you move from small q to capital Q and small p to capital P via a canonical transformation, then the Poisson bracket will be the same. Okay. So that means if QP was 1 and you also have capital Q and capital P, Poisson bracket equals 1, then you can prove that the transformation is canonical, that the transformation that connects Q and capital Q, small p and capital P, a canonical transformation. So these are the two statements. So let us focus on the statement number 1 and let us try to see how it is generally possible to prove that. Okay. So again, I will use the notation that my x vector is my old variable. So this is my q and p. There might be multiple components, and my y vectors are my new phase space coordinates. So capital Q, capital P. Okay. So the first of all, the Poisson bracket in terms of the old coordinates, which I denote by let's say fg, okay, in terms of my old coordinates. So in terms of qp. So this qp in the subscript means that I am taking the Poisson bracket in terms of the old coordinates. So this is del f del q del g del p minus del f del p and del g del q. Okay. So you can write it as um, oops, you can write as a row matrix. So here you put del f del q and then del f del p. You have seen this before probably, and then 0 1 minus 1 0 and del g del q del g del p. So that is what is meant by that. So if you write it in a notation of x and y, so this, so remember this small q is basically x1, the small p is x2. So I can write this in a compact notation. So summation over jk del f del xj then gamma jk. So this matrix is gamma, um, and then del g del xk. Okay. Now our job is to relate this Poisson bracket to the Poisson bracket in terms of the new coordinate. So I want to find out the connection that this how this is related to fg in terms of the new coordinates qp. Now my claim is that if small qp and capital QP are connected via a canonical transformation, then the values of these two Poisson brackets are the same. So that is what I intend to prove at the end of the day. Okay. So I first for that I wrote expressed my Poisson bracket in terms of my old coordinates as this. Okay. Now again, since the coordinate transformation, or not the coordinate transformation, the phase space coordinate transformation can be expressed as, so right, like x is a function of the new coordinates, like conversely. So what you can write, so this will imply if you try to find out del f del xj. Okay. So that can give you, so in terms of y, you can write summation over, let's say, L del f del yl del yl del xj. Okay. So this is this should be via the chain rule of partial differentiation. You can have that. Okay. So I will replace this here and also actually in here in a similar form. Okay. So with this I can rewrite that my fg in terms of the old coordinates, okay, is basically just I take out the jk summation. Now this del f del xj is again summation over L. Then you write del f del yl del yl del xj. So this is your del f del xj. Then of course, as you had, this is gamma jk, and you can have in the same way, in the same speed, you can have this to be del g del ym, oops, and then del ym del xk, where you have summation over m again. Okay. So so this thing I have written like this. Okay. Now again, if you remember, then these are precisely my elements of the Jacobian. So this is my JLJ, and this is JMK. Okay. So in the next step, I use a cute little trick. So I take out this summation. So I take out, say, LM summation. Okay. And I take this JK thing, JK summation here, and then I notice that inside this thing, inside this JK summation, I have this thing. So this is JLJ gamma JK. This is JMK. That means J transpose KM. I write that. Okay, and let me put this within curly brackets, and then whatever remains, I have remaining these things, this and this. Sorry, not this. So I have the remaining quantities as del F, del YL, and del G, del YM. All right. Great. So again, this is the LMth element. So if you take also include the sum. So this is the NLth element of J gamma J transpose. Okay. But if my transformation is canonical, then this is equivalent to gamma LM. Okay, that was the condition for my canonical transformation. So I am assuming that from going from small q to capital Q and small p to capital P, I am doing it via a canonical transformation. All right. So so I can write this thing as summation over Lm del F del YL gamma Lm del G del Ym. Okay. Now compare this this expression. So you should compare this expression with this expression here. So if del F del Xj gamma Jk del G del Xk is the Poisson bracket with respect to my old coordinates, then this thing, this del F del YL gamma Lm del Ym, summation of L and M, is the Poisson bracket with respect to my new coordinates. So this is precisely equal to the Fg in terms of my new coordinates, that are Q and P. Okay. So essentially, we have showed that if the phase space coordinates are related via canonical transformation, then the Poisson bracket relations do not change. Okay. Now you can prove the converse as well. So if my Poisson bracket relations does not change under the phase space coordinate transformation, then the transformations would be canonical. So I leave that as an homework. Okay, you just try at home, and you can write that. Okay. Now let us think about the point transformation as well. So in point transformation, what I had, which was the transformation of the coordinate only. So this is the coordinate transformation. So you showed that that if qk goes to a new coordinate qk, which is a function of the old coordinate and time in general. So I am not considering time dependence as of now. So I will remove this and I will just consider on this thing. So this, under this point transformation, we showed that the Lagrange's equations remain unchanged. Notice that I am only changing the coordinate. I am not changing my momentum. Okay, so if you like, so basically capital Pk is still equals small pk. Okay, so I am not changing my momentum. Okay, so if I have a transformation like this, when I only change my the definition of my coordinate, generalized coordinate, then I noticed that Lagrange's equations hold true under such kind of transformation, and I would naively expect that since the Hamilton's equation essentially follow from Lagrange's equation, it's a special case scenario of Lagrange's equation, it will also hold true. But I also know that for Hamilton's equation to hold true under a new coordinate system, the transformation must be canonical. So what I am suggesting here is that if you transform only coordinates without spoiling the momentum, so this type of transformation is a special class of canonical transformation. So this type of transformation should be canonical. Okay? So let us try to see that if I only change my coordinates, then mm, the resulting transformation is canonical. So first, let us find out that from here I can write down that qk dot equals summation over j del qk del qj dot. Okay. And from here, basically, I can write down, since the qj dot dependence is only here. Okay, I can write down del qk dot del qj dot, or rather a particular ql dot, okay, would be given by del qk del ql. Okay. So this is the important relation, and it has to do with the fact that it doesn't depend explicitly on time. So this is the relation that I am going to use in a moment. There's a dot here. Okay. So this is my first thing, and similarly, you can also prove that the inverse is also true, that del qk dot and del ql dot is also equals del qk del ql. So I will be using that. Okay. Now remember that I should not have said that this capital Pk is equal small pk. So this capital Pk, what I meant is that the capital Pk I do not transform. By do not transform, I mean that I accept whatever is given by this. Okay. So I accept that in terms of the new coordinates, whatever is my del L del qk dot, I accept that to be my capital Pk. So this is a bit a special case of the earlier phase space transformation that I was talking about. In the general phase space transformation, the transformation of qk has nothing to do with the transformation of pk. You could transform them independently, and the condition that this transformation will be a canonical transformation was given by the condition that your Jacobian is a symplectic Jacobian. Okay. Good. Now, so this is my generalized momentum. So, so then let me try to find out then. So this pk is equals del L del qk dot, which is, again, if I expand from the new coordinates to old coordinates, so this is del L del QL del QL del QK dot, okay, plus del L del QL dot and del QL dot del QK dot. because remember L is a function of q dot and t. So this is a function of q and q dot. I am not assuming explicit time dependence for now. Okay. So first thing you should note is that this term is 0 because QL does not explicitly depend on Q dot. So Q doesn't depend on Q dot. That's why that is 0. So then finally you have this Pk is equal summation over L, and this is your small PL, right? So your old PL. This is PL times that is just del QL del QK. So that is the thing I wanted to arrive at. Okay. So if this is the thing, then you can now check what is your um, Hamiltonian, what is your Jacobian. Okay. So let us try the one-dimensional version. So let us try that is only 1p. So you can generally do it for k equals 1 to 9. So p is equal small p del q del q. Okay. So how do you construct your j? So j is constructed as this. So j would be given by so the first term is del capital Q del small q. Then I guess here you have del capital Q del small p. Then you have del capital P del small q, and you have del capital P del small p, right? So first thing you note is that this term is 0 because my transformation only depends on coordinate. Okay, so the simplified version of j is given by del capital Q over del small q 0. For now you keep it as del small p del q, and del p del small p you write it from here as del small q del capital Q. All right. So now your job will be, so if this is j, you have to check that j times gamma times j transpose. You have to calculate and you have to show that this is equals to gamma. So if you find that, if you find this thing that j gamma j transpose equals gamma, then okay, hold on a minute, I have to take this call. Hello. Yep. So sorry about that. So j gamma j transpose is equals gamma. So you have to show that. So if you, I mean, if you calculate, it will turn out to be gamma. That means that such a transformation, so the transformation defined by these two relations are indeed canonical transformation. So any purely coordinate transformation and then leave the momentum as it is, like whatever comes, you accept it in terms of the new coordinate, should be a canonical transformation. And that's why this is an alternative way of saying that why under point transformation Lagrange equation remains the same. And from this exercise, you also learned a more general feature of if you are given a general transformation in terms of Q and P, so suppose in the questions of net or other things, you would be given transformation of this nature. So QP and capital P is equals again a function of small q and small p, and you have to check whether the transformation is canonical or not. And the recipe to do so would be you just calculate this Jacobian. Okay, you calculate this partial derivative and simply check this. Okay, so this is I mean as simple as it is. Okay, so this is a very common question in your competitive exams. So you may want to practice some of this type of problems. Okay, so I will pause for a brief moment here and let me check if there are questions.
Sir?
Yes.
So when you said like under the point transformation, the Lagrangian will not change. It is the like the alternate.
I didn't say the Lagrangian will not change. I said the Lagrange's equation will not change.
Equation, yes, sir. The Lagrange's equation. So, sir, I mean Lagrange's equation is like invariant under any kind of like coordinate transformation. Shouldn't it
Yes.
be like the Hamiltonian's equation will be invariant under this special case?
Yes. Yes, because Hamiltonian equation also follows from Lagrange's equation essentially. So that point transformation that you learned under which Lagrange's equation retains its form is a special class of canonical transformation under which you do the transformation in this way. So you only modify the coordinates. Okay. So basically you are going from say Cartesian coordinate to polar coordinate here, and you are redefining your generalized momentum accordingly. So if you go from say xy to r theta here, then the momentum will be defined as like one momentum will be r dot and another momentum would be r squared theta dot up to a mass scale. Okay, so those are your those are your momentum. Okay, so you do not change your momentum freely. You do not redefine your momentum freely. You accept as it comes as a result of the coordinate transformation.
Under this point, I mean coordinate transformation.
Yes.
And so in the very last line, so can you go on that page?
Yes.
So you said that like we have to check if these capital Q and capital P are canonical. So I mean, you said that this J and gamma and J transpose equation should be like valid for that. But shouldn't it be like, can we like easily calculate it like by taking the Poisson's bracket of Q and P with respect to like Q and P directly without like introducing the
Yeah, you can use the Poisson bracket. It's the same thing. So this is
yes.
the Poisson bracket you are checking actually.
Yes, sir.
But you have to take the Poisson bracket with respect to the old coordinates.
Q and
Remember
P,
that.
Q and P.
Okay, so you have to take the Poisson bracket Q of P with respect to the basis small q small p.
Okay, sir.
Okay. So you cannot just do that del q del q del p del p. You should not do that. If you do that, then that is zero. That's not properly defined. So when you check the fundamental Poisson bracket relation, you have to do with respect to the old coordinates. Okay. So that is basically what you are checking here. So this J are basically those things that you use in Poisson brackets. These are the things that you use in Poisson bracket. So the checking Poisson bracket also means calculating these derivatives.
So actually, you wrote in the very in the initial steps of the canonical transformation. From there, I continue.
Yeah.
So where you wrote about the Poisson brackets are invariant under CT canonical.
Yes. Yes. Poisson bracket are invariant under canonical transformation. Yeah. You can do that. So you are basically doing the same thing, right? So the Poisson bracket is also related by this matrix gamma. Okay. So if the Poisson bracket remains invariant, what you are assuming is that this combination is equals to that combination. So that is what you are saying. So you do it any way you want, not a problem.
Okay.
But remember to take the Poisson bracket with respect to the old coordinates, because see, with respect to the new coordinates it is always 1. Okay, so QP with respect to capital Q capital P, okay, so this is always 1. So you have to check basically this is indeed equals QP with respect to your old coordinates. Then only you are suggesting that Poisson brackets are remaining invariant. Calculating only this doesn't give you the full picture. I mean, this is obviously equals 1. Is that clear?
Yes, sir.
All right. So now I will discuss I will discuss something that how can you easily construct a canonical transformation. Okay, so constructing canonical transformation. Okay, so I will be using the the concept of a generating function. Do not confuse this with generators. Okay, these are not generators. The generators are associated with group theory. These are generating functions for canonical transformation. So the canonical transformations basically relates new phase space coordinates with your old phase space coordinates. Okay. So the essential idea is that if I can suitably define a function that is a function of both old and new coordinate system. Okay, so the idea is that so you define a function f. It has one old coordinate. By coordinate I mean phase space coordinate. Okay, and one new coordinate. Okay. And if you and you just suggest, so you just assume that the other coordinates are related to the first derivative of this function. So let me give you an example. Suppose there is a function, say f1, which is a function of small q and capital Q. Okay, and you want to you just assume that these two relations hold, that small p equals del f1 del q and capital P equals minus del f1 del capital Q. Okay, so this defines your so this actually defines a transformation, right? Because this del f1 del q, this will be a function of small q and capital Q, right? So what I can do here, I just write it as, say, small f1 small q capital Q. So if you invert this relation, so what I can say is that, so you can invert this relation to get Q is equals as a function of small q and capital P. So once you have that, then you substitute this q here, and then you will have small p, sorry, capital P also as a function of small q and small p. Okay, so if you have these type of relations, then you can manipulate it algebraically to express as a coordinate transformation, in phase space. Okay, so this together defines my coordinate transformation. The point I am trying to make is that if you obtain these relations from these parent equation, that where p is related by this and small p is related by this. Okay, so these are and these things are generated from a single function which I call f1. Then the resulting transformation that you get will always be a canonical transformation. So this will always lead to a canonical transformation. So this is an easy way to kind of generate canonical transformation. Okay, to come up with canonical transformation. Okay. So to prove that it is indeed canonical transformation, again I would like to find out what is my Jacobian, and the Jacobian, as I told you, is given by del q, del small q, del q, del small p, del p, del small q, and del p, del small p. Okay. So okay. Or so if you calculate this, then you will have something, and then you have to calculate J gamma J transpose, and you have to check that that is equals to gamma. You will again find that the condition for that to hold would be simply as already pointed out by one of you, is del q del small q del p del small p minus del q del small p del q del uh, sorry, del p del small q equals 1, and this precisely is the Poisson bracket between q and p, but with respect to the old basis qp. So we have to check that this indeed holds. Okay, so our objective is to calculate this thing. So for that, let us compute the derivatives first. So first we note that this del p del small p uh, will be given by, since p is a function of, so if I use this relation here, okay, so I can write it as minus del 2 f1 del q2 times del q del p, because uh, I am taking the partial derivative with respect to p, and this p and q are my kind of variables here. And another thing I have to calculate is del p del small q. So that will be given by, first of all, f1 itself depends on q, so that gives me del 2 f1 del capital Q del small q minus again del 2 f1 del q2, and then del q del small q. So I need to now plug in these two things. So I first plug in del p del small p here. So this will replace this. And the other thing, del p del small q, would be replaced here. Okay. So if I replace those things, then I can check that this qp with respect to my old basis, a small q small p, should be given by this thing, del 2 f1 over del small q del capital Q times del q del p. Okay, so you have to reorganize this a bit. So you write it as del q of del f1 del q and then del q del p. So this del f1 del q, according to my definition, is my small p. Okay, so this thing is equals to del of small p del capital Q times del capital Q del small p, and this is equals to 1, at least when I am doing the calculation for a single variable. So this is basically del p. So this is del p over del p, and that is equals to 1. Okay. So so this is what we have here. So since this is equals to 1, I am convinced that the transformation that is generated from this F1 is indeed a canonical transformation. So if we construct a transformation, a phase space transformation that comes from functions like this, then I will have the resulting transformation will be a canonical transformation. Okay. So the definition of this f1q small q is not unique. Of course, if you check your last homework problem in the in your homework set 5, so you can also construct f2 as a function of small q and capital P. So remember, capital P was related via this relation. So again, you use your knowledge of Legendre transformation to figure out what will be the definition of this f2 in terms of f1. So this should be f1 rather. I think it might be f1 plus capital P. I am replacing with capital Q. So f1 plus p times q, and this should be an explicit function of small q and small p. And if you do that, the relations will be small p equals del f2 del q, that remains unchanged, and capital Q will now be del f2 del p. Okay. And similarly, you can also define f3 and f4. Usually, those are denoted by, so f3 is a function of small p and capital Q, and f4 is a function of small p and capital P. Okay, so these are the 4 different possibilities for generating functions that you can define, and each of them will entail different relation. So depending on the canonical transformation at hand, either f1, f2, f3, or f4 might be more convenient to use. So you have to look at the canonical transformation itself. Then you will find out which of these generating functions to use. And these generating functions will be your stepping step. Like this is the first step towards the Hamilton-Jacobi theory. So from this you will need this thing to learn about Hamilton-Jacobi theory, which will exploit the essence of canonical transformation. Okay, so remember, as I told you, in the Hamiltonian formalism, in the Hamiltonian formalism, the cyclic coordinates. Hold on a second. Dealing with cyclic coordinates becomes really convenient, and what you try to do using this canonical transformation is that you from from small q small p. Yes. From this small q small p, you go to a new coordinate capital Q capital P, so that in terms of your new coordinates, this q becomes cyclic. So if you can somehow make this capital Q to be cyclic, then you know the new momentum p will be a constant of motion. And when I introduced the Hamiltonian formalism, I explained that what kind of advantage cyclic coordinates give you in Hamiltonian formalism. It effectively reduces 1 degree of freedom. And that is the essential point of Hamilton-Jacobi theory. So Hamilton-Jacobi theory in general lets you construct wisely. So how do you switch from this set of coordinates to this set of coordinates, such that in terms of my new phase space coordinates, some of my coordinates become cyclic. And if it happens, then our life becomes simplified. So I can solve a very complicated problem in a relatively easy manner. Okay, but then why this canonical transformation is necessary? So remember, to fully use the power of my cyclic coordinate, I need to make sure that in terms of my capital Q and capital P, my Hamilton's equations of motion still holds. And the condition for that, as I told you, that if you want this capital Q and capital P to be still maintaining your Hamilton's equation, then this transition from small q small p to capital P must be in a way such that the transformation is canonical. Now we have found the condition for the transformation to be canonical. The condition for the transformation to be canonical is J gamma J transpose equals gamma. Okay, the Jacobian being symplectic. But you cannot just blindly try an arbitrary transformation and then check every time whether this holds. For example, you cannot just play trial and error game. Okay, so this trial and error game would be like, so you define any arbitrary things. Let's say capital Q equals small q sine p, and capital P equals small p cosine q. Okay, so this is a transformation. Now you have to know whether this transformation is canonical or not. Okay, so then you just go on and check whether this holds or not. But you cannot do that every time. That will take too much time. So you cannot just come up from vacuum from and whatever transformation you write, and then you check whether this transformation is canonical, and if it is, then you go on with it, and if it is not, then you discard it. You do not want to play such trial and error game. So you want a more convenient way of producing canonical transformation, and that's where these functions f1 f2 f3 f4 comes in handy. So these lets you produce. So this basically gives you a guarantee that if you produce your transformation from this from a parent function like this, then the transformation that you end up with is guaranteed to be canonical. Now, now that I have a guarantee of having a canonical transformation, the only thing I need to do is that I have to choose this f1, f2, f3, and f4 wisely. So how to choose this f1, f2, f3, and f4 wisely, such that when you land on a new coordinate, that capital Q, it becomes cyclic. Okay. That's the idea. So that is the essential idea. So you use your f1, f2, f3, f4, any one of them actually, wisely, such that when you land on a new coordinate, the one of the coordinates or one or more of the coordinates are cyclic, and that is the essential point of this Hamilton-Jacobi theory and action angle variable. So that is the essential message I wanted to give in. So I will stop my discussion of canonical transformation here, and perhaps, yeah, I should stop the lecture now. And let me know if you have questions until this point. Any questions? All right. So I hope. So by the way, after this, this will be taken forward by Dr. Pakira, and I will take a class tomorrow, and I might need one extra class. I will tell you that tomorrow, and the next week, I think the 22nd is Wednesday, right? So I don't think it would be a good idea to take classes on Monday or Tuesday. So do you want classes on Monday or Tuesday next week? All right. So in that case, if I cannot finish up what I intended to do, then please make sure that I get an extra class before the end of this week. So maybe let's say Saturday afternoon. Is everyone okay with the idea that I might take an extra class on Saturday afternoon? I'll let you know the time. Is it okay? All right. So the plan is that I will start tomorrow an introduction to what is called continuum mechanics. Okay. Or sometimes it also known as the classical field theory. I wanted to talk about this so that you have some relativistic formulation. You get used to those things. The thing that I was supposed to do, but I didn't have time to do. But I do think that uh, you should be able to self-study those chapters. Is the topic of moment of inertia and rigid body motion. Okay. So the thing is that the moment of inertia, the definition and principal axis transformation. Okay, then Euler rotation. This should be easy. Okay. And some problems regarding that. So that is basically, I leave it for you self-study. There is a whole chapter that I could not cover here. I don't think there was enough time. Just to be clear that I will not give any questions from moment of inertia or principal axis transformation in the mid semester if you are worried about that. But you should study it at your own interest. It has some interesting things to cover, and more importantly is that the exams, let's say, what are the exams, NET or GATE, whatever you would be aspiring for, uh, they have sometimes questions from that. So make sure that you cover that chapter. Okay. And I guess some of you had some idea from your BSc courses, right? This moment of inertia, how to find moment of inertia for a three-dimensional objects. And finding the moment of inertia matrix and then diagonalizing it and finding the principal axis transformation. So hopefully that is all right. So is that all right with everyone? That you would be able to self-study this chapter? Okay. Um, this should not be very difficult. So try out. All right then. So I now stop recording and